Hey everybody, Chris back again with a new Proto Tech Tip, and for this week we're going to be diving back into GD&T and talk about a concept called datums. So let's get into it. So not long ago, we did a Proto Tech Tip which went through the basics of geometric dimensioning and tolerancing. If you've missed that video, just check out the description below for the link. So in this video, I'm going to talk about a concept called datums. But first, I want to explain the feature control frame. A feature control frame is a standardized way to call out geometric dimensions and tolerances. Depending on the type of characteristic, it may reference no datums for form tolerances or up to 3 datums. Now, a datum is a theoretical reference point, a line or surface on a part that serves as the origin for measurement in manufacturing. It acts as a frame of reference against which other features are defined and inspected, ensuring consistency in how parts fit and function together. Datums are usually selected from important functional surfaces or features, such as a flat face, a hole, or even an axis, and they're labeled with capital letters. So when you place datum symbols on a drawing, you're instructing the manufacturer on how to align the part within this framework. This makes sure that not only the person making the part, but also the person measuring it are holding it the exact same way. Now, datums are usually labeled A, B, and C if there's only 3, but parts can have more datums. Plus, different control frames might actually reference different datums depending on what's actually needed. Now, in mechanical engineering, degrees of freedom refers to the number of independent parameters needed to fully define the position or motion of a mechanical system, encompassing both translational and rotational movements. Datums are applied in a specific order: primary, secondary, and then tertiary, to progressively constrain a part in space. Together, they remove the 6 degrees of freedom that any rigid body possesses. The sequence of the datums in a datum reference frame is going to be intentional and meaningful. Now, a manufactured part will never be perfect. When inspecting a manufactured part, the inspector must compare the imperfect part with the theoretically perfect version shown on the drawing. This can only be done by creating a perfect grid to measure the manufactured part against. This perfect grid is the datum reference frame. So a datum reference frame is the coordinate system created by the datums specified in the part drawing. Now, the order of the datums referenced in a feature control frame is going to be important for the measurement of the part. The primary datum, which is the first one in the control frame, will be the first to be constrained. It does require at least 3 points of contact and at least 3 controls and 3 degrees of freedom. The secondary datum, which is the second datum listed in the control frame, will always be perfectly perpendicular to the primary datum within the datum reference frame. The secondary datum requires 2 points of contact and is constraining an additional 2 degrees of freedom. So the tertiary datum, which is the third datum listed in the control frame, will always be at 90 degrees to the primary and secondary datums in the datum reference frame. It is the last datum to be fixed during the measurement, and the tertiary datum does require 1 point of contact and is constraining the last degree of freedom. So remember, a datum callout order is going to be a big deal. Now, a common mistake, though, in reading GD&T drawings is assuming that the alphabetical order of datums, the A, the B, and the C, is arbitrary, but it's actually not. The order in which datums appear in the feature control frame dictates the order of precedence. So the order matters because the parts are going to be imperfect. So in this example, both scenarios we aligned first to datum A. However, for the left part, our primary datum aligns to B and then to C, where the part on the right side aligns to C first and then to B. And you can see how that will affect our inspected values here. So changing the order changes the alignment, which changes the measurement results. So a part might pass inspection with an A, B, and C order, but it might actually fail with a B, A, C order. When it comes to GD&T, not all datums work the same way. Some datums, called designated datums, don't actually need any specific geometric tolerance on their features before being used. These are the actual physical surfaces, the holes, or the edges on a part. They're directly used and tied to the datum feature and can be used right away to establish the datum reference frame. On the other hand, though, we have qualifying datums. There are a bit of a difference here because they do require the geometric tolerance on the datum feature to meet the certain criteria first. Basically, you've got to ensure that the geometric tolerance is met before you can use the datum for referencing. Now I want to go through some quick rules of thumb. So when you're selecting datums, choose them based on the function. That is, how the part sits, locates, and clocks within the assembly. The datum order here defines the setup order, so it's best to prefer features that are stable, accessible, and repeatable. You should also use datum modifiers, though, when you want the inspection to reflect the actual clearance in the real-world assembly. Now, as part of our high-velocity mass customization model at Protocase and Protospace MFG, inspection is included in our list of services. To get to know more about our inspection services, including how we use things like GD&T as an inspection language, email our team over at info@protocase.com or info@protospacemfg.com. All right, so remember to keep an eye on our YouTube channel for more tech tips on GD&T coming in the future. Until next time, take care.